All right, so this is the fifth online sort of canned lecture that I'm putting together. So we're now leaving moment diagrams. As you'll see, we need the moment diagrams to to complete this sort of activity. But that's not really the goal here. The goal is to calculate displacements. So we've talked a lot about how forces are distributed within a structure, in particular internal actions like moments and shears. And now we're going to use those to calculate how a structure deforms. And for the time being, we're going to deal with flexural displacements. So that is displacements due to bending. Just so you're aware, 99% of displacements in civil structures are actually due to flexure. So very few due to axial or shear, and we try to avoid torsion, so there's hopefully not a lot of displacements due to torsion. Okay, so we're going to start this by reminding you of, what did I do here? All right. By talking about the definition of curvature, right? And so we said curvature is the change in length, change in slope per length. Okay. And we said that guy equals, so this would be the change in slope per the change in length, right? D theta dx. And we said that equals what we refer to as curvature. It also equals 1 over rho, right, where rho is the radius of curvature. So if you go back to that set of lectures where I drew the sort of deformed beam, we showed the center of curvature, and we dimensioned everything. This was sort of early on when we were developing the expression for stresses within flexural stresses within a beam, right? So that was our curvature, change in slope per length, right? So the other thing I want to do here, and I'm going to do it, let me just draw the whole thing. Let's see. Okay, so this is strain and this is position. This is the strain diagram, right? So curvature is also equal to that slope, right? We also said that curvature is the slope of the strain diagram. So I'm looking at my notes and confusing myself. So if you remember when we solved for the stress within a flexural member, it was sigma equals my over I, right? And that means that the strain is just my over ei, right? And it means that the slope of this, which is just the strain over y, so I'm going to bring the y term to the left side of the equation, and what I'm left with on the right side of the equation is m over ei, and that is equal to curvature. Right? And so what we are talking about here, well, let me keep going, and if I need to come back, we can come back and do that. So what we're going to do here is we're going to set that guy, which I'm going to call 1. That's one way of representing curvature. And that guy here is a second way of representing curvature, right? So what I'm going to write is that, and I'll do this, I guess, in black, I'm going to write that d theta dx, that's curvature, equals m over EI. That is also curvature. Right? And we are also going to recognize that theta is the derivative of the elastic curve. So this V is what we're going to call the elastic curve. That is the deformed shape, right? So all we're saying here is if my deformed shape looks something like this, right, I can take 2 points of that deformed shape, right? And I can, let me do this, I guess, in green. Right? I can take the slope of that line, right? And the slope of that line, which we're going to call theta here, right, is actually this distance here. Let me extend this a little bit. So this distance here, which I'm going to call dV, right? So this guy is sort of V1 and V2. Don't ask me why it's V. Generally, U is a displacement in the X direction, V is a displacement in the Y direction, and W is a displacement in the Z direction. So that's dV, and then the horizontal distance between these points, which is this guy here, is dx. So the change in horizontal displacement or position is divided into the change in y displacement, right? And that gives me theta. And that's what that elastic curve V is. And so if I take the derivative of that, dV dx, I get theta. And if I then summarize this by plugging all of that in, I get d squared V dx squared equals m divided by EI. So I'm going to box this a couple times. Right. And where V equals the deformed shape, deformed shape, sort of AKA, also known as the elastic curve. And so what we're going to do as we move forward with this is we're going to, you can sort of see where this is going, we're going to, I'm going to give you a structure, we're going to draw the moment diagram for the structure. That moment diagram, the equation of that moment diagram is going to go right there. That's m, right? And the EI is a constant, right? So this is a constant. This is the moment diagram. So you can see it will be a function of x, right? And then we're going to integrate it twice. And when we integrate it twice, this term here, d squared v dx squared, is going to just become v, right? So every time we integrate it, that moment diagram is going to go from, say, 5x to 5x squared over 2 plus a constant, right? So we're going to integrate it twice. We're going to get 2 constants of integration. And then we're going to look at boundary conditions in order to solve for them. For example, simply supported would say that the displacement at both sides of the beam are 0, right? So that would give me 2 equations I could solve for my 2 boundary conditions. If it's a cantilever beam, I would say that at the fixed support, the displacement is 0 and the slope is 0. So I would say v of, say, x equals 0 is 0, and I would say theta of x equals 0 is 0. Okay? Again, I get 2 equations, and I can solve for my 2 constants of integration. All right, so next time we will do